Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to represent a topic Introduction of Digital Electronics or Fundamental of Digital Electronics. The subject Digital Electronics, BTech Electronics and Communication fourth semester. So digital electronics, in the subject we are going to cover the for the topics that is logic gates, uh, Boolean algebra, specification, combinational circuits, flip-flops, sequential circuits, memory components, integrated circuits. Logic gates. Digital computers imply that the computer deals with digital information, that it deals with the binary information that is represented by binary digits. Why binary instead of decimal or other number system? Consider electronic signal 0, 1, 2, 3, 4, 5, 6, 7, its signal range, binary 0 and 1, and this is in the octal. Consider the calculation cost, add, and this is the calculation cost formula. Binary digital input, and through the gate, uh, it's going to be convert out binary digital signal output. Types of basic logic blocks, combination logic blocks whose output logic values depends only on the input logic value. Sequential logic blocks whose output logic value depends on the input values and state stored information of the block, that is on the prior information. Also the sequential logic circuits and the combination logic circuits having a slight difference, that in sequential logic circuits a prior value which is already stored, depending on that it is depending that what the output going to come out. Function of gates can be described by truth table, Boolean function, and K map or Karnaugh map. Combinational gates, these are the some basic gates: AND gate, OR gate, uh, inverted or NOT gate, buffer, NAND gate, NOR gate, XOR, exclusive OR gate, XNOR, exclusive NOR or equivalence. And the formula function is given, the symbol and the function is given, and the truth table of the particular gate is given in the slide. As you see that AND, its function is equals to x equals to a into b, or x equals to ab. That is, the symbol is represented by a d, and the two inputs a and b give one output x. So x is equals to 0 0 0 1, a 1 0 1 1. The 1 and 0, only one in the case of 1 1 the output is 1. Otherwise, because it is a multiplication, so 0 0 becomes 0, 0 1 becomes 0, 1 0 becomes 0, and 1 1 become output 1. Similarly, it depends upon the function, that is OR gate. Its function is x equals to a plus b. Inverted or NOT gate, x equals to a bar. That is what you are going to give single input, it is complement of that. Uh, Buffer is just same as it, a x equals to a, whatever a input, the x will become out as same. NAND gate, that is x output equals to a bar, ab bar, and we more deliberately can write as a bar plus b bar. Nor a plus b bar, or we can write it a bar into b bar. Similarly, or XOR and XNOR. So these are the truth tables. So these are the basic gates. Boolean algebra. Boolean algebra. Algebra with binary, Boolean variable, and logic operation. Boolean algebra is useful in analysis and synthesis of digital logic circuits. Input and output signals can be represented by Boolean algebra. Uh, and um, Boolean algebra is useful in analysis and synthesis of digital logic circuits. Input and output signals can be represented by Boolean variables, and function of logic digital logic circuits can be represented by logic operation, that is Boolean functions. From a Boolean function, a logic diagram can be constructed using AND, OR, and not. Truth table, the most elementary specification of the function of digital logic circuit is the truth table. Table that describe the output values for all the combination of input values called mean terms and input variables gives 2 to the power and min terms. So binary logic deals with the variables that make two discrete values, one for true and zero for false. A simple switching circuit containing active elements such as diode and the transistor can demonstrate the binary logic, which can either be on, switch closed, or off, switch open. Electrical signals such as voltage or current exist throughout the digital system in either one of the two recognizable values except during transition. The switching function can be expressed with Boolean equations, truth table, logic diagrams, and K-map. Truth tables offer an easy means of representing any switch functions of n variable. The transformation of equation to truth tables or K-map is little difficult. However, the reverse process of finding equation from tables and map requires min term, max term, and simplification methods. Boolean algebra can be used to simplify the design of logic circuits. However, this method involves lengthy mathematical operations. An alternative method called the K-map can be used for the simplification of Boolean equation with up to 4 input variables. The use of K-map would become difficult if there are more than 5 input variables. Hence, it is better to employ the Quinn-McCluskey method, which is tabular method of minimization. These minimization techniques reduce the requirement of hardware. Development of Boolean algebra. Mathematical George Boole or mathematician George Boole invented a new kind of algebra, the algebra of logic, in the year 1854, properly known as or popularly known as Boolean algebra or switching algebra. He stated that the symbols can be used to represent the structure of the logical throughout. Boolean algebra differs significantly from the conventional algebra. This algebra deals with the rules by which the logical operations are carried out. Here, a digital circuit is represented by a set of input and output symbols, and the circuit function expressed as a set of Boolean relationship between the symbols. Boolean expressions are basically defined by stating that a constant is Boolean expression and variable is a Boolean expression. So we can say that logic circuit design, as you see, truth table, then come to the Boolean function, and the Boolean function can represent the truth table. And from these, we are going to draw a logic diagram. So, for example, we had taken in the diagram that three inputs x, y, z with three gates, and the f is the output taken. So we know the function of each gate, and the input is inserted or input is given at the value of x, y, z in the terms of 0 or 1. So these are 3. So 2 to the power 3, that is 8 combination can be done. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 0 1 1 1 0 1 1 1. So these are the expected input, possible inputs, and the output come out to be depending upon the final combination. So usefulness of this table: simplification of Boolean function, derivation of equivalent Boolean function to obtain logic diagrams, utilizing different logic gates, ordinarily ANDs, ORs, and inverters, but a certain different form of Boolean functions to obtain circuits with NANDs and NORs, application of De Morgan's theorem. Many different logic diagrams are possible for given functions. So these are the some logical diagrams or logic diagrams for different possible given functions. We can, it's our own choice that how many types of gate and what the arrangements of the gates we can done to get the output according to the boolean function. A boolean function of a digital logic circuit, a boolean function of a digital logic circuit is represented by only using the logical variables and or an invert operators. Logical operations can be expressed and minimized mathematically using the rules, laws, and theorems of Boolean algebra. It is convenient and systematic method of expressing and analyzing the operation of digital circuits and systems. Boolean algebra uses binary arithmetic variables which have two distinct symbols, 0 and 1. These are called levels or stages of logic. For example, a binary 1 represents a high level and a binary 0 represents a low level. Uh, Properties of Boolean algebra. Boolean algebra is a mathematical system consists of set of two or more distinct elements, two binary operators denoted by the symbol plus and dot, and one unary operator denoted by the symbol either bar or that is complement. These satisfy the commutative, associative, and distributive absorption and senses and idempotency properties of the Boolean algebra. So, commutative property, associative property, and distributive property are the properties. Now, De Morgan's theorem. So, De Morgan's theorem, uh, two theorems that are important that part of Boolean algebra proposed by the De Morgan. The first theorem states that the complement of a product is equal to the sum of the complement. That is, if variables a and b, then AB bar can be written as A bar plus B bar. That is, break the line, change the sign. The second theorem states that the complement of the sum is equal to the product of complements in the equation. From this, we can write A plus B bar can be written as A bar dot B bar. The complement of Boolean logic functions or logic expression may be expanded or simplified by the following steps of De Morgan law. That is, change the sign or break the line, change the sign. Okay, it's a very simple technique. Truth table, unique, give Boolean function, many different expression can exist. So simplification from Boolean function, finding an equivalent expression that is least expensive to implement. For a simple function, it is possible to obtain a simple expression for low cost implementation. But with the complex function, it is very difficult task. K-map is simple procedure for simplifying Boolean expression. So K-map to table, and by Boolean function, we can make a K-map, and the K-map give the simplified Boolean function. K-map is basically a technique to reduce the Boolean function. So the simplification of the switching function using Boolean laws and theorems become complex with the increase in the number of variables and the terms. The K-map technique provides a systematic method for simplifying and manipulating switching expression. In this technique, the information contained in a truth table or available in the product of sum or sum of product form is expressed on the K-map. The K-map is actually a modified form of truth table. Here, the combinations are conveniently arranged to aid the simplification process by applying the rule AX plus AX complement equals to A. In n variable K-map, there are 2 to the power n cells. Each cell corresponding one combination of n variables. Therefore, each row of the truth table, that is for each min term, and for each maxterm, there one specific cell in the K map. The K maps for 2, 3, and 4 variables are shown in figure. The decimal codes corresponding to the combination of variables are given inside the cells. The variables have been marked as A, comma, B, comma, C, comma, and D, and are the binary number formed by them are taken as AB, ABC, and ABCD for 2, 3, and 4 variables respectively. The 3 and 4 variable K-map show that column and row headings used in representing the cells are cyclic or unit distance code, which results in adjacent cells. Differing in just one variable, this helps the grouping of the adjacent cell and in their uh, uh, simplification by the application of the rule ax plus ax bar equals to a. In addition, the left and the rightmost cells of the three variable K map are adjacent. For example, the cells 0 and 4 are adjacent and the cells 1 and 5 are adjacent. This is because each pair differs in just a single variable. In 4 variable K map, the cells to the extreme left and right as well as those at the top and bottom most positions are adjacent. So, came up for an Kinsey, or we can say that the phenomena takes place and appears to be or assumes to be like that hole is moving. When electron is captured by a hole, the covalent bond is again re-established. The conduction of electrons are found in and above freely in conduction band. The hole exists in and move in the valence band. Distinction between metal insulators and semiconductor. So, difference between metal insulators and semiconductor. We had discussed about the metals, insulators, and semiconductor. And metals, insulators, and semiconductor are characterized on the basis of energy band diagram, and that is the most important base to differentiate the metal insulators and semiconductor. There are many energy bands in solid as there are energy levels in parent atom. The electrical conduction properties of solids are concerned. Only the valence band and conduction band energies of the electron are considered. Completely filled bands and completely empty bands do not contribute to electrical conduction. So, by the means of this statement, we can say that any completely filled bands, that is, their orbital or their electronic configuration is almost complete, they are not going to take participate in electrical condition because they are not having a free electrons, and we had already discussed that free electrons or the valence electrons plays a vital role in the electrical conduction. And if empty bands are there, that means there are no short of electrons present over there. So the empty bands do not contribute to the electrical conduction. Obviously, when the electron is not there, then how the electrons are going to be moved or to take part in electrical conduction? The electron in the innermost filled shell do not take part in conduction process. Again, the innermost shell electrons do not take part because they are tightly or mostly attracted by the nucleus, and the attraction force is so high that they cannot take participation in conduction process. So we conclude that in conduction process, the valence electrons or free electrons are to be contributed. Next, the electrons in conduction band are free and move easily under an electric field. The electrons in valence band are attached to the lattice and are not free to move. If they acquire sufficient energy to cross the forbidden energy gap, they occupy the conduction band and states are available for conduction. So, a minimum amount of energy is there, and if that amount of energy is acquired or gained by an electron which is externally provided, then and then only conduction of electron takes place. Okay. Prior to that forbidden energy gap, they remain in their own still position. They are not going to participate without acquiring the energy. On the basis of band theory, solids are classified into three categories, which we had already seen, that insulators, semiconductors, and conductors are differentiate on the basis of band theory. And just a small review once again to give the classification of insulator through the some pictorial representation. Insulators are those materials in which the valence electrons are bound very tightly to their parent atoms. Hence, very large electric field is needed to remove them from attraction of nuclei. The band picture of insulator is shown in the figure. Valence bands and conduction band, and the gap between these two bands is denoted by Eg, known as forbidden energy gap, and the gap is very wider, as you've seen through the diagram. So a very high amount of energy is required to contribute the electron from valence band, or in conduction theory, to move the electrons from valence band to the conduction band, because the energy or forbidden energy gap is very much high. So in their stable state, and this much of amount of energy is not possible to give to the insulators. If you just give the amount of energy to cross over the valence band electrons to the conduction band, and if you provide that amount of energy or greater amount of energy to the insulators, then the covalent bonding breaks down and electrons acquire the very high energy and do participation in conduction. But that much amount of energy taken by the electrons dissipated more heat, and that heat destroy the, or we can say that uh, burns out. So at the very high level of forbidden energy, the insulator get burns out. So, and that amount of energy is not possible to provide. Features of insulator: a full valence band, an empty conduction band, and band gap energy is of 5 to 10 electron volt. So this much of energy is to be required for moving a electron to take participation in conduction from valence band to the conduction band. Very high resistivity of order of 109 ohm centimeter. Some samples at high temperature and under sufficient electric field, some electrons may move from valence band to conduction band. Hence, insulators show small conductivity at high temperature. Yes, the temperature plays a important parameter or important role uh, in contributing the conduction or phenomena of conduction of electron from valence band to the conduction band, because temperature is also a short of energy, and whenever the energy above the room temperature is provided, then their characteristic properties of the electrons or the atoms changes, and due to the changes in their characteristic properties, there is some sort of energy gained by the electrons, and they start moving from valence band to the conduction band. Now, semiconductors. A semiconductor material has electrical properties between those of insulators and conductors. So, semiconductor is the element which lying between the insulator and conductor, and almost all properties which show in the insulator and which we are going to discuss in conductors, and the middle of those two, all the properties lying in the or plays a important characteristic in semiconductors. So semiconducting material has electrical properties between those of insulators and good conductors. The band diagram of semiconductor is shown. So in the figure shown to you, the conduction band and valence band is separated by a energy gap or forbidden energy gap, and by a amount of energy, but it is somewhat lesser than insulator. Features of semiconductors: almost empty conduction band and filled valence band with very narrow energy gap. That is, the energy gap is almost equal to 1 electron volt, and we had seen the energy gap or energy gap in insulators is between 5 to 10 electron volts. So the difference is very large. Okay, at 0 degree Kelvin, the valence band is 0 Kelvin, the valence band is completely filled and conduction band is empty. So at the temperature 0 Kelvin, we find the observation that valence band is completely filled and the conduction band is empty. But as the temperature increases, the electrons in valence band acquire enough energy to cross the small energy gap and move to the conduction band. Thus, the conductivity of semiconductor increases with temperature. So we can say the semiconductor in a semiconductor, the conductivity increases with temperature. Next, the electron moving to conduction band leave behind positive holes or created a vacancy in valence band. Hence, semiconductor current is the sum of electron and hole current flowing in opposite direction. The resistivity varies from 10 to 12 to 109 ohm centimeter. Example: germanium having energy gap is of 0.7 electron volt, and for silicon it is of 1.1 electron volt. Now conductors. The conductors have large number of free electrons available for electrical conduction. Conduction may be defined as solids characterized by a single energy band called conduction band, which is partially filled at any temperature. Alternatively, a conductor as a solid in which the conduction and valence bands overlap and there is no energy gap between the two bands. So, in the case of conductors, the conduction band and the valence band are overlap to each other, and at the room temperature, we can say that the conduction of electrons takes place, and a very small amount of energy is required to move a conductor or to move electrons in a uniform direction, and that contribute the electric current, because the electronic configuration of conductors or the conducting materials or the conducting elements are having the large number of free electrons. Their electronic configuration, by observing their electronic configuration, we will see that their free electrons are in very large quantity, and we know that for conduction or conduct electricity, electrons plays a vital role in electrical conduction, and free electrons plays a vital role in electrical conduction. So the conductors are having abundant amount of or a large number of free electrons, and due to that the conduction band and the valence band overlaps to each other. So this is the diagrammatic representation of conductor in which there is a zero energy gap, or forbidden gap is zero, because conduction band and valence band overlaps to each other. As there is no forbidden gap, there is no structure to establish hole. The total current is simply due to the flow of electrons. Example: lithium, beryllium, sodium, and many more elements in the periodic table is characterized on the basis of electronic configuration as the conductors. Types of semiconductors. Now, after come to the difference between insulators, semiconductors, and conductors, semiconductors are of great importance in day-to-day electronics world. So, semiconductor is divided in two types of category. One is intrinsic semiconductor or pure semiconductor, and the other is extrinsic semiconductor or impure semiconductor. Here, extrinsic or impure means that is you are adding some dopant, or impurity means the dopant, not the impurity like some wastage. You are adding some external elements to the pure element, then that category is considered to be the extrinsic semiconductors. It has been already discussed that semiconductor is a material whose electrical properties lie between those of insulators and conductors. A semiconductor has almost filled valence band and almost empty conduction band with a very small energy gap between the two. The semiconductors are of two types: pure or intrinsic. Second is doped or extrinsic or impure. And this extrinsic or doped semiconductor is further classified into two more categories. One is p-type semiconductor and second is n-type semiconductor. So as the research and goes on continuous on the semiconductors, then through that research they conclude to the some devices formed by the semiconductors, and they play a vital role in electronic communication and electronic world. So semiconductors are the basis of electronic engineering, electronic applications, or electronic appliances. Next, pure or intrinsic semiconductors, semiconductor like germanium and silicon has crystalline structure. As we observe the periodic table, the atoms are arranged in third group, fourth group, and fifth group are of crystalline structure, and the fourth group element has a purely crystalline structure. Their atoms are arranged in ordered array known as crystal lattice. These materials are tetravalent in nature or tetravalent in nature with four valence electrons in outermost shell. So the electronic configuration of fourth group element is having four valence electrons in their outermost shell. The neighboring atoms form covalent bond. The neighboring atoms form covalent bond by sharing four electrons with each other, so as achieved stable structure. A two-dimensional structure of germanium crystal lattice is shown in figure. So I'll show the lattice structure of a germanium. So this is the lattice structure of silicon. Just wait a minute. So germanium, instead of germanium, I'm showing the lattice structure of silicon. So all the silicon atoms in a crystal lattice or in the ordered form are arranged like this. Every silicon atom is bonded to its neighbor silicon atom. If I'm talking about the central silicon atom, it is having four valence electron in its outermost shell, and these four outermost electrons make a covalent bond with their adjacent silicon atoms. And if a small amount of energy is given to the intrinsic semiconductor, then as you observe through the figure that energy among all the four electrons or any electron get that energy and move to the conduction band and create the space over there, and it is noted with a vacancy name designated as vacancy, and this vacancy is generally known as hole. Next, in which the circle represents the atom core consisting of the nuclei and the inner 28 electrons. Each pair of line represent a covalent bond. The dot represent the valence electrons. The intrinsic semiconductor is the material in its very pure form. The band diagram of pure semiconductor is shown in figure. Sorry. Yes. Again, this is the pictorial representation of a semiconductor, pure semiconductor, in which valence band and conduction band and the central to these bands at the very center position one dotted line is marked, and this line is known as the Fermi level. So whatever the energy given to the semiconductor, if that sufficient amount of energy is taken by the valence electrons, then they cross the Fermi level and reach to the conduction band and plays a vital role in conduction of electricity, or electrical conduction takes place. So Fermi level is a criteria or a parameter defined to cross the barrier for playing a vital role in conduction of electrons. At zero temperature, all or 0 Kelvin temperature, all the electrons are paired and are contained in completely filled valence electrons. So, by the above figure, we come to know that at 0 Kelvin, all the electrons are covalently bonded and contained in the completely filled valence band. No electron is free for conduction band. Hence, the conduction band is completely empty. The energy gap between the two bands is small. Example, no, the energy band gap between two bands is 0.72 electron volt for germanium. At 0 Kelvin, the energies of these magnitudes are usually not acquired by the applied field. Hence, the valence band remains full, the conduction band empty, and material behave as insulator. At a room temperature nearly 300 Kelvin, some of the valence electrons acquire thermal energy greater than Eg, that is 0.72 for germanium, and hence they can jump to the higher conduction band. So the thermal energy provides the threshold or thrust to cross over the threshold, that is the Fermi level, and the electrons start jump from valence band to the conduction band. And in this way, by acquiring the sufficient amount of energy, electrons take participation in conduction. Next, they now act as free electrons and can move under the influence of a small applied field. The absence of electron in valence band is the hole under the influence of electric field. The electron from the neighboring covalent bond may fill this vacancy, that is, hole moves in a direction opposite to electron motion in valence band. The hole moves in the same direction as would the positive charge carrier. Hence, in semiconductors, there are two types of charge carrier. The total current is the sum of electrons and hole current. In intrinsic semiconductor, electrons and holes generated in pairs. Obviously, they are in pairs when electron take participation in conduction. It left a vacancy over there, and that vacancy is known as hole. So, when any electron take participation in conduction, it creates a vacancy or a hole. So we can say that in intrinsic semiconductor, electrons and holes are generated in pairs. So, law of mass action, according to the law of mass action, number of electrons into number of electrons and number of holes, number of electrons into number of holes is equals to Ni square. The law of mass action says that the conservation of law, according to the law of conservation. Next, At any given temperature, the number of electrons in conduction band and number of holes in valence band are same. With the rise in temperature, more and more electron hole pairs are formed and more charged carriers are available for conduction. Hence, the conductivity of intrinsic semiconductor increases with the rise in temperature. The intrinsic semiconductors have low conductivity. The most important, the intrinsic semiconductors have low conductivity because the participation of electrons, the valence electrons are very few or very less. So the conductivity is very low. Doped or extrinsic semiconductor. So thank you. This is all for the today's lecture, and I will continue this topic in the next lecture. And in further continuation of this topic, we are going to start with the new topic, that is superconductors, and the questionnaires and quizzes related to this topic. So thank you all. Thanks a lot.